Okay guys, in this video I'm going to teach you about what's known as the law of sines. And it turns out the law of sines can be used with any type of triangle, not just right triangles, and I'll explain why that works later. In the next video that you'll watch today, I'll go through the apply it problems, and then at the end of the period you'll be working on your homework for the remainder of the class period. Now this picture is a little bit misleading because it kind of looks like it's saying it's an equilateral triangle. So let's go ahead and fix those arcs. Let's make them all different. Okay, so the law of sines can be used for any triangle, and what you do is ratio of opposite parts basically can be made using the sine ratio. And compare them. So you have to be able to identify what is opposite from what. So let me show you what I mean. So we would say that the sine of angle A, and go ahead and write this please, over side little a is equal to the sine of angle B over side little b, which is equal to the sine of angle C over side little c. So you can see that what makes a ratio would be a pair of opposite parts with sine. So the sine of this angle compared to its opposite side, see little a is opposite from that side, makes the first ratio. And then the sine of angle B, so here's angle B right here, and the side opposite from that is little b, is equal to the sine of angle C, this angle right here, compared to the side opposite from it, little c. So it's important that we're able to identify our opposite pairs of parts in order to use the law of sines. So let's practice that for a moment. In this triangle, I want you to identify the side that's opposite from angle E, the side that's opposite from angle D, and the side that's opposite from angle F. I'll give you a moment and then we'll talk about it. Okay, across from angle E, here's angle E, so we go across from it, would be side DF. And we probably would nickname that side little e because it's located across from angle E. Opposite from angle D, here's angle D, so opposite from that would be side EF. And we would nickname that lowercase d. And finally, across from angle F, we have side DE. And we would probably nickname that side lowercase f. Okay, so you're probably wondering at this point, isn't trig just for right triangles? How is it that we have something that works for triangles that are not right? And it turns out that we actually can take any triangle, such as this random ABC that I just drew, put in an altitude, so I drew an altitude, and it will create two right triangles. Now these two right triangles we can form sine ratios with, and so that's what we're going to do right now. So I'm going to call this altitude h, as in the height of the triangle. If I'm focusing on this angle, this is my theta right here, the sine ratio, oops, let me get the lowercase letters real quick. Across from angle A, we have side A. Across from angle C, we have side C, and across from angle B, we have side B. And no, I don't expect you to be writing this down. I'm just showing you where the law of sines comes from, so you're not confused why we are suddenly using sine with non-right triangles. Okay, so again, if I'm focused on A as my theta and I want to set up the sine ratio, I would say that the sine of angle A is equal to opposite is h and the hypotenuse is little c. And then I can go ahead and solve that equation for h by multiplying both sides by c, so I get c times the sine of angle A is equal to h. I can do the same thing with this theta if I'm looking at angle C and that right triangle. So I can say the sine of angle C in the other little right triangle is equal to opposite is h again, and the hypotenuse of that one is a. Then if I multiply both sides by a, I now get h is equal to a times the sine of angle C. All right, you'll notice that both of the equations that I've written are set equal to h, which means we can set them equal to each other. So I can conclude that C times the sine of angle A is equal to A times the sine of angle C. Right? It's getting closer to looking like the law of sines, but we're not in ratios yet. So what I can do at this point is divide both sides by C, little c, and I can also divide both sides by little a. And so what I end up with is the sine of angle A divided by little a is equal to the sine of angle C divided by little c. And I could repeat this process using a different altitude so that I get B in this also. But this is just a little demonstration to show you that we are using this for the full triangle, which is not a right triangle, but it comes from breaking the triangle up into right triangles. Okay, go ahead and play the next video, which will say law of sines apply it problems.